Everything is better as a double.
Double stuffed Oreos.
Double bubble chewing gum.
Double Dutch jump rope. A double-double.
Or even double integrals. Now you may be asking yourself, what are double integrals? And I will answer that in time, but first let's start by doing a quick review of the definition of a definite integral for functions of single variables. First, when working with the integral of the function f of x, line 1, we know that x exists in the interval between some number a and some number b, line 2. Note that this does assume that a is smaller than b, line 3. We then use this expression to determine the area under the curve of f at x, which we do by breaking up the interval of a to b into n number of subinterval rectangles of width delta x, line 4. And then we choose a point, x asterisk, which is the midpoint of each rectangle, line 5. Now what we have is the complete list of all the ingredients we need for a definite integral of a single variable. Now that we have all of our ingredients, each of the rectangles, as seen here, has a height of f at x asterisk and width of delta x. So we can then calculate and use the area of each of these rectangles to approximate the area under the curve, using equation number 1. To get the exact area, we then take the limit as n approaches infinity, which leaves us with the definition of the definite integral, which, you guessed it, is equation number 2. So that's cool and all, but this video focuses on double integrals, because as we know, everything is better as a double. So now, let's take a look at how to integrate a function of two variables, f of x and y, line number 1. With functions of one variable, we integrate it over a one-dimensional space, and so it makes sense that when integrating a function of two variables, we will integrate over a region of two-dimensional space, known as R2. Line 2. We will start out by assuming that the region in R2 is a rectangle, which we will denote by line 3. This means that the range for x is between a and b, and for y is between c and d. This is line 4 and line 5. Now that we understand all this, and have the components of a double integral, let's start out with the graph of the surface S, given by graphing f at x over the rectangle R, as seen in this diagram. When constructing a double integral, it is helpful to think of the question as trying to figure out the volume under a surface. And so here, we will figure out the volume of the region under S and above the xy plane. We will first approximate the volume much as we approximated the area for single integrals. We will divide up x into n subintervals and divide up y into m subintervals. This will divide up R into a series of smaller rectangles, and from each of these, we will choose a point in the center of these rectangles indicated at x asterisk, y asterisk. Now, over each of these smaller rectangles, we will construct a box whose height reaches the surface at its midpoint. Each of the rectangles has a base area of delta A and a height of f at x asterisk and y asterisk. So the volume of each of these boxes is its base area times its height. With all this mess, I mean math, taken into account, the volume under the surface S is then approximately the expression given by equation number 1. We will have a double sum once we will add up the volumes in both the x and y directions. To get a better estimation of the volume, we will make both n and m larger and larger to get the exact volume. Therefore, we will need to take the limit as both n and m approach infinity. This is given by equation number 2, which, voila, is the equation for a double integral.
You can use Maple to better visualize double integrals. Let's say you are trying to take the integral of f of x and y equals x squared plus y squared as x goes from -2 to +2 and y goes from -3 to +3. First, make sure you are in the math mode. Then go to Tools, Load Package, and click Student Multivariate Calculus. Type in the integrand, in this case x squared plus y squared. Next, right-click on this function and go to Tutors, Calculus Multivariate, and click Approximate Integration. This opens up the Approximate Integration tutor. Notice that our function f is in this first box and that the graph of the function f is displayed on the left. Adjust the bounds on x and y by typing them into the correct boxes. In this case, x goes from -2 to +2 and y goes from -3 to +3. Click Display and look at how the graph of f and x changes. You can adjust the n and m values to change the number of boxes used to approximate the double integral. Notice that when you do so, the approximate value box, which is the volume of all of the rectangular prisms, changes, but the actual value box, which is the exact value of the double integral, does not. As you can see, when you increase m and n, the approximate value approaches the actual value of the double integral. Hit Close to insert the plot into the Maple command window. There are lots of other ways to do integrals in MATLAB. First, type in your integrand. Next, right-click on the integrand, then go to Constructions, Definite Integral, and click X. Type in the lower and upper bounds of x, in this case -2 and 2, and click OK. Now do the same thing again. Right-click on the integrand and go down to Constructions, Definite Integral, and this time click Y. Type in the bounds on y, which were -3 and +3, and click OK. You can get Maple to evaluate this integral for you by right-clicking once again, selecting Evaluate, and voila!